All right, so let's have a look here at some more of this deflection. Now, we went through this problem here, and obviously it was an awful lot of calculus that we did. Let's have a look at perhaps a more straightforward way of doing it, and that uses these tables. They're posted in Moodle. So what we have here are two tables. One side of your handout is simply supported beams with different typical loads on them. And what you've got there is you got the beam, you've got the slope at the left side, slope at the right side, maximum deflection, and the deflection at the center. That's what's listed. All right. And then you have a similar table on the other side for cantilever beams. Beam, slope, and deflection. All right, so first off, be sure you're using the right type of beam, simply supported or cantilevered. Right? And what these tables can do, once you learn how to use them, is help you avoid getting into that to find a simple deflection. Okay, so let's see what we can do with these. So I think, now some of these page numbers might be a little different because I've changed this packet around over the years, but I think this is what we're dealing with here. Okay, so that's 900 is the page now. It's not 915 anymore, it's 900. All right, let's figure out how much that cantilever would deflect if you applied these loads to it. All right, so we got a beam cross section is 4 inches by 6. We can find the moment of inertia, which we'll need to know. That will affect how much it bends. So BH cubed over 12 is 72 inches to the 4. We've got E, so this is 29 times 10 to the 6 psi. Now what we want to do is find the angle, which is the slope, because remember an angle in radians and the slope are pretty much the same thing for small angles, and delta B. We want to find both of those, all right? So the first thing when I'm doing these English ones, especially imperial units, is I want to get everything converted. I want pounds and I want inches. And remember to do that for everything if you've got a problem in imperial English units. So 8 feet is 96 inches. A kip is 1,000 pounds. So that 4 kip load at the end is 4,000 pounds. And then I've got 3 kips per foot, which is 3,000 pounds per foot, and a foot is 12 inches. So that comes out to be 250 pounds per inch. All right. So before I get into any of this stuff, I want to be sure that I've got the proper units set up. Okay. All right, now what I'm going to do is that's a cantilever beam. I can see that hatching to indicate a support at A. So what I want to do is pull off the cases that I would use to figure this out. A case is just the loading situation for it. So what I've got for that loading is I've got a cantilever beam with a uniform load, distributed load, plus a load at the end. So there's nothing fancy here. I just have to add those two situations together. That's all I got to do. Okay? So I'll take both of them and add them up. So I'm going to use the cantilever with a distributed load. The angle for that is WL cubed over 6EI. And the delta for that is WL to the 4 over 8EI. And then I'll use the situation there with a cantilever with a load at the end. The angle or slope at the end of the beam is PL squared over 2EI. And the delta for that is PL cubed over 3EI. So I just take the tables and I look at the formulas and write them down, basically. All right, so those are the two sets of formulas that I'll use. So I got the slope angle formula, and I've got the deflection formula. Okay. Now all I got to do is just plug the numbers I've got into the formula, and then I'll just add the results because the net deflection will be the sum of the two deflections I've got there. The net slope will be the sum of the two slopes. That's all there is to it for this type of problem. Okay. All right, so if I want the total angle, then I just add the two together. Now, the one thing on this is you got to take whatever numbers you're given off the formula, and you have to, look at them and be sure that they're actually applying to what we're wanting to do. So, for instance, the slope here they're both going to be negative slopes. If you look at that beam when you load it, those loads are going to cause it to bend down, right? So you just add the two negative slopes together. But remember that they're negatives. And you just plug the numbers in. It's really about all there is to it. All right. So we got negative WL3 over 6EI minus PL squared over 2EI. And we add them together. So minus 250 pounds per inch times 96 inches cubed over 6 divided by E divided by I, and then subtract off 4,000 pounds for the point load times the square of the length, 96 inches squared, divided by 2 EI. When you combine those two together, it's negative 0.0265 radians, which is negative 1.52 degrees. So what's going to happen here when you load this beam up, as shown there, is it's going to be bending down, and at the end of the beam, if you project that out, that's 1.52 degrees. The slope is negative 0.0265, okay? So that's what would happen with this beam, with our models here, okay? So we're doing all right with that? Okay. Now you can also get the deltas, okay? And it's just the same kind of deal. You just add the effects together. Not much to it, really. So delta B will be minus WL4 over 8EI minus PL cubed over 3EI. You just plug the stuff in. So the thing is, I just want to be doing all of my unit conversions at the beginning. I want to get everything into pounds and inches and just be sure that I'm accomplishing that. All right, so what's going to happen there is that beam's going to bend down, and that's 1.83 inches that'll come down. Okay. So that might be a good model there if you have a cantilever porch. You're going to have the distributed load from all the material you built the deck, right? The deck might be a better word. The deck out of, the beams and the flooring and all that. That would get you a distributed load like you see on the left. And then maybe you figure for your worst case scenario, you've got all these people on the rail at the end looking out at something, and that would be the point load. Yeah, the two together. That's about it. And so that's all you got to do with that. Okay. So we're seeing that deck would sag almost 2 inches. Okay. All right. Now, let's look at some other cases here. Okay. Now, these can get a little tricky. That one's a straightforward one. You just add the two effects together. And, I imagine when you start working, a lot of the stuff you're doing is going to be pretty straight up, You don't get into real crazy loading situations. But let's have a look at 914, just for fun here, okay? Now, let's say we've got that. So the uses of this thing can get a little bit trickier sometimes. So let's have a look at this one. Looks like that. Or no, it doesn't. I'm further down the line here. There we go. I'm on this one. So I've got I I've got E is 40 gigapascals. I've got a cantilever with no load on it 3 meters out. And then 2 meters out, I've got 40 kilonewtons per meter. All right. And I've got I figured out. Now, if you look at your cantilever table there, unfortunately, I don't see that loading condition. I don't see a nice table that'll knock that out for me. Okay. Now, what I do see is one table that tells me what delta would be if I had a beam that was fully loaded for its length. So if I have a cantilever beam and I load that thing up, I have a table that will tell me what delta would be. Okay. Now, what I've also got is another table that will tell me what would happen here if I had a cantilever with only a partial load on it. So if I have that cantilever beam with a load over some part of the beginning, I've got a table that'll give me delta for that. But I don't have a table for my particular situation. So what I can do with this is I can take that top table, figure up delta for it, and then come in and figure up delta for the red loading there on the bottom, the partial loading. And what am I going to do with that partial loading? Subtract it, yeah. See, so sometimes you got to use these tables kind of creatively to get to what you want, okay? So that's one example. Okay? So I would find, yeah, question there?
If you were using the fully distributed load like it said to, and then you use that 40 kilograms per meter across the load,
Yeah. Then, yeah, like what we're going to do here. You take the 40 kilonewtons per meter, and you run it through the whole beam. Then you take a piece out of it. Then you find 40 kilonewtons per meter for just the first 3 meters. That would be a negative number because that would push the beam down, but you actually subtract that number, you know, from your original negative number, if you know what I mean. So that's the deal. So if you find delta at the end of the beam for 40,000 newtons per meter over the 5 meter span, that's WL4 divided by AEI, that would push that end of the beam down 0.1736 meters, so 17 centimeters. Okay. But then what you can do is find what that partial loading would do. And what the partial loading would do would push it down 4.25 centimeters. Notice that's a little trickier situation, so it's got a more involved equation. Wx1 to the 4 over 8EI. That looks like it's finding the delta for that first 3 meters is what that's doing. See, that looks an awful lot like the equation above, doesn't it? And then what you're going to do is take the slope there, the Wx to the third times 6EI, and you're multiplying it by that second offset. You're using slope is delta y over delta x. So if you want to find delta y, you take the slope, which is actually this equation, times the delta x, which is that second x extension out. It's unloaded. Okay. And when you do that, you get 0.0425 meters, okay, when you plug all that stuff in. So if you want to find the total delta of that point B or C now also notice that you got to be a little careful with how you approach these. You can call different points different things. On the table, they call the end of the beam B, but we're calling it C. So don't get confused just because we call it delta B. It might mean something different on the table. Use the positions on the table, so to speak. You know, don't get hung up on the subscripts, what the letters are. All right, so if I want to find that total delta, it's going to be less than if it was fully loaded. If it was fully loaded, it's 0.1736. But then I can subtract off that piece at the end, which is 0.0425. So I'll take negative 0.1736 plus the 0.0425, and I'll get delta C. At the end of my cantilever there, it's negative 0.1311. Okay? So that's one example of a more advanced use of the tables. Sometimes you have to work with subtraction to get to your answer. All right. Now, we good with that? Okay. Now I got another example before this, actually, that's actually a little bit more involved yet. And that's these numbers on my slides aren't right. It's 910. So what I got there is a simply supported beam with a moment at A and an overhang at B. Okay, it looks like that. So let's find the slope at B and the deflection of C. Now to do this, I'm going to have to use the charts pretty creatively because there isn't an overhang chart. Okay. So I'm going to have to deal with, kind of work through what I got to handle the fact I don't have a chart for overhangs. Oh, let's see. The other thing I'd point out is, just before we get into this one, on that last one, see, that was the one we did with calculus, and that's something I just want to show you, just while I'm thinking about it. That's what it took to solve that problem using the charts, what you see right there. A bit of algebra, but nothing too horrible, okay? I mean, and compare that to what we had to do to solve it using the charts. You know, it's night and day, the difference between the two. That's what had to be done to solve it using calculus, okay? Same problem. So you can kind of see the advantage of learning these charts. You know, so I just thought I'd point that out while I'm thinking about it. All right, so to get back to this one, now this one's going to be a little trickier, this one, okay? All right, so now what we're going to have to do is kind of do this piece by piece. The first thing I'm going to do is handle that overhang. And what I'm going to do is treat that beam initially like it's a simply supported beam that goes from A to B. And I'm going to find the moment that gets turned into it at B on account of that overhang. So that overhang is 3 meters and 4 kilonewtons per meter. So that's going to cause a moment about B of 4,000 newtons per meter, which is the 4 kilonewton per meter, times the 3 meters, which is the span over which it acts. So that'll get me 12,000 newtons pushing down, and that'll go through the centroid of that rectangular loading diagram, which is half of 3. It's 1.5 meters over. So that gets me 18,000 newton meters clockwise about B. Okay? So that's the moment that that overhang turns in at B. So the first thing I'm going to do is use that diagram that I showed down below on page 910, where it has those 2 moments on either end. Okay? So what I'm going to deal now with is a simply supported beam with a moment on either side, a couple. And see, I've got a table for that. And what I've got then is A and B at the bottom of the simply supported table. And for the slope at A, I got ml over 3 EI, and for the slope at B, I've got ml over 6 EI. So let's see what's happening there for that, where those table values come from. So I'm looking at this is right off the table right here. So from the charts. Now, a good visualization, I think, for this is to take like a wrench, like what you get to open the valve for the water in front of your house, like a T-bar wrench. I've seen spark plug wrenches like this. I've seen some lug wrenches. They don't make them so much anymore, but the T-wrenches for lug nuts were that way. Okay? So it's just a bar with something that'll fit on a bolt at this end right here. So this would have the socket right there. And then the other end, you got like a T-bar. Okay, think of turning that as shown here with a couple. If you remember couples from statics. So what you're going to do, you're going to take that T and turn it this way. What's going to happen to that beam if I do that? Let's say that beam is somewhat light and flexible, it'll bend. What's going to happen at A? Is it going to bow down or up, or what's going to go on there? So if I take that and turn it, so I've got my beam like this, and what I'm going to do is turn it in that direction. Y'all seeing that? That's going to bow that down. And notice where it's more pronounced. It's more pronounced where I apply the moment, right? And then it kind of smooths out as I get further over. So that's what's going on there, is if I turn that wrench like that, I'm going to bow this side down at a pretty extreme amount, and then it's going to slowly kind of straighten out as it gets further over. So I get something like that. So I've got a steeper slope here that's actually negative. That's ml over 3EI, right next to where I apply the moment. By the time I get to the opposite side, the angle is half as much. It's ml over 6EI. That's what's going on there. So think of these not as being left and right on the chart, but as being adjacent to where I apply the moment and opposite of where I apply the moment. Right next to where I apply the moment, I got the biggest amount of slope. As I get further out, I got less. Okay? So that's gonna inform how I calculate this stuff here on the two beams down below. Why don't you go ahead and sketch in what those deflections would look like on those beams if you applied those two moments. And again, for me, it's helpful to think of taking a wrench with a T on it and applying that torque. That one's counterclockwise. This one's clockwise. In both cases, what will happen to those beams?
So, yeah. Well, I did this, and then you triangle on top of this, so that, and then you go there.
Yeah.
Are you gonna do something like that on the test where it's gonna be this one, and you have to mix it with
That'll be additive, yeah. There could be different things to do, and break it up into pieces.
Right.
Just take the individual pieces and put them together. And actually, you wouldn't have to come up with a total load here. You could just take this case and figure it out, and then take that case and figure it out, and put them together. It's not like you have to do any sort of sensory thing.
Okay.
You know what I'm saying?
Yeah. Perfect.
All right. So this one's going to bow up here, right? You all good with that? Something like that? And the other one will bow up too, but it'll be more extreme on this side, right? And it'll kind of flatten out on the other. So something like that. So they both look like negative slopes to me. So the first one is on the far side, the opposite side. It's away from the moment. So it's ml over 6EI. And the second one is next to the applied moment, so it's ml over 3EI. And they're both negative because of the way those moments are turned in. They'll both bow the beam up, which gets you to a negative slope. Okay? So that's how that works. So when I run the numbers on those, I get negative 0.0045 radians and negative 0.00225 radians. So I just add the two together, and it's negative 0.00675 radians is what I get for the sum. Okay? And again, kind of that idea of using a T-bar wrench there and turning that moment in is helpful to me to kind of see which way they're going to bow. And what I have here in class is a long ruler that's made of real thin metal, so I can bow it real easily. It's like 1.5 feet long. If you had a little ruler here in class, that wouldn't bother me. It helps to visualize. And I'm not shy about using little visualization tools like that when I'm working. That's fine. Just be sure you get it figured out. Okay. So that's negative 0.00675 radians. So that's the angle that we'll see in this beam, okay? So that angle right there is 0.00675, okay? And that's caused by the two couples at either support. All right, now if I've got that and I know that angle, which again, a small angle in radian and a slope are pretty much the same thing. See, I can find delta y, okay? Because what the slope, which is the angle in radians, which I'm calculating here, which is equal to the slope, is delta y over delta x, right? So if I want delta y, which is equal to what I call delta, that's the slope times delta x, okay? So if I take that angle in radians times the 3 meters, that will get me how much the end of the beam would go down on account of that slope. Okay? You okay with that? If I can find the slope at that support, I can figure out the deflection of the end of the beam just by using the fact that slope is delta y over delta x. So delta y, which is what I just call that lowercase Greek delta, is just the slope times delta x. But I got more going on than that, though, because I have to look at what caused that couple at the support, which I'm calling B there. And what caused it is a distributed load going from B to C. So not only is that thing bending down and extending out in a straight line, which I would pick up by doing this little slope times delta x thing, but it's also got a load on it. And what that's going to do is bend it down and curve it. So I got to consider that too. I have to consider both effects. The angle times the offset distance, which I guess that should be better said, the slope times the offset distance. And I've got to consider the fact there's a load on that. And the best way I can model that is to treat it like a cantilever. Okay? So I've got this beam that's running over that point at B, a continuous beam. That acts kind of like a cantilever support at B. And that beam, as it extends beyond B, will bow down on account of that load. And that will be minus 4,000, or excuse me, minus WL4 over 80I. And I'm getting that from the cantilever table with a distributed load on it, the third case down on the cantilevers. So when I consider that, it's negative 4,000 newtons per meter times 3 meters divided by 8, divided by 200 times 10 to the 9, divided by 8 times 10 to the minus 5. That's negative 0.00253. So not only will that beam go down on account of the slope times the distance, it also drops further because there's a cantilever load there, uniform load. So I take those two effects and add them together. I take the 0.02025 meters and I add in the 0.00253 and get the two together and get negative 0.02278 meters. So that thing's going to drop 2.278 centimeters is what my calculations here lead to. Okay. So, we got any questions on that? All right, so so that's a little bit on deflection there. When I get you some of these, we'll have a look at them on Friday. No, these will be due when we have our final. Now our final's on Wednesday at 3. So that'll be due Wednesday the 20th when we have our final. And we'll cover those on Friday, okay? They're all written up for you. That's on page 30A, B, and C. And we'll cover them pretty well. So